Okay. So can you see the screen? Is it visible?
Yes, sir.
Okay. So I have perhaps not yet. Did I send you some recording of this performance class so far? Did I send any? Did I send any recording so far?
No, sir.
No. Acha. So I shall be sending these recordings now, and this document also I did not send. Actually, there are some error here. It will not correcting this error is a bit difficult because now it is not admitting any changes because of some reason, because this was actually developed by some other uh, people. So some of our employee, he has created this, he has done for it, and there are some errors. So I shall try to rectify this error and then we shall send you. Okay. So now stability we have started. Equilibrium criterion we have explained, and from this diagram I have explained. Then the expression, mathematical expression for condition for equilibrium criterion has been also explained here. Integrating it will be d delta dt square. It has been written in this way, so by mistake he has done it. So I will try to correct this. Okay. So basically integration from delta 0 to delta. What is this delta? This delta is the final delta. That is at delta 0, the machine is rotating at synchronous speed. At delta, again it is rotating at synchronous speed. So these are the two extremes between which the swing will be taking place. Okay. And obviously, the stable point, if a new stable point exists, that will be in between delta 0 and then delta. That is between the two extreme points between which the machine is swinging, between which the rotor is swinging. Delta, new stable operating condition will actually exist. So here, this two delta indicates the starting point and the end point of the swing. At this point, at delta 0, the machine is rotating at synchronous speed. At delta, it is also rotating at synchronous speed. So what does it imply? D delta dt obviously is 0 for stability. The condition is written here. This is, again I am repeating, is d delta dt square. So integration PA d delta from or between these two angles, delta 0 and delta is 0. That indicates that total energy input or total energy extracted from the system is 0 between these two points. That means energy actually delivered to the system must be equal to the energy extracted for the system. What is this energy? This energy is the extra energy. Obviously, at delta 0, when the machine was rotating at synchronous speed, there it was having some stored kinetic energy, and that stored kinetic energy is the kinetic energy at rotate speed, and this should always be the kinetic energy of the machine because it is rotating at synchronous speed. It is maintaining synchronism. Okay. So if any extra energy is inserted into the rotor of the generator, it has to be extracted from it. This is the, you can say in one word, if we say what is the condition for stability, transient stability, this is the condition for stability. If any extra energy is imparted into the rotor, that has to be extracted from it. This is the meaning of this expression, delta 0 to delta delta, the integration over PA delta is 0. Okay. So this, then I started this explaining this example where initially there was a change in the input from 50 megawatt to 80 megawatt. Okay. And we had to check whether the system will be stable or not. Actually, explaining these examples, it is always better on in the classroom if we take the help of blackboard and chalk. Here, since this is done, it is so somewhat difficult because if I write something and explain something, it always becomes better. So here I shall be explaining the basic things. calculation and other things you will be able to do, because these things are given, you will be able to understand. So what is basically done, you see that in the first case, when the stability limit, steady state stability is being stated to be 100 megawatt. That means this is the peak of the power angle curve is given. 50 megawatts the generator was delivering, and that means input was also 50 megawatt, and the abrupt increase in input by 30 megawatt. So input becomes 80 megawatt. Then we have to check whether the machine will be able to maintain synchronism or not. So to do this, what is required? You see that from delta 0, this is the initial operating angle. Now this becomes the new power input line. So obviously this triangular shape, this area, which is very similar to a triangle between AGBA, this will indicate the area where the energy will be actually imparted into the rotor. Why it is energy imparted into the rotor? Because energy fed to the rotor. Why? Because this is the power input line and this is power output curve. So input is greater than output. Obviously, there is excess energy. Where this energy will go? It will be going to the rotor of the generator. Generator rotor will speed of the rotor will accelerate, speed will increase, and it is happening here. So this energy indicates the energy delivered to the rotor of the generator. Now, for maintaining stability, similar such area should be available. So if you can ensure that there is an area available which is at least equal to this area, and where the rotor will be decelerated, then it ensures that the generator will be able to maintain synchronism at least at the first swing. So that's why what we should do here. You see that when the generator rotor will cross this point B, obviously it will cross this point because input is greater than output, generator is accelerating. Speed here was synchronous. At this point B, speed will be above synchronous. So generator rotor will cross this point, delta will increase. As delta increases, output output curve. This is power angle curve is the output power curve. So it becomes greater than the input power line. So generator now will decelerate. So you can say that what is the available decelerating energy? Generator rotor must complete deceleration and must regain synchronism before point C is reached. Why we are seeing this? Because if the generator rotor cannot regain synchronous speed at this point, then that means if it crosses this point, then again input line will be greater than the output, So again the rotor will accelerate. So if the speed is above synchronous at this point, it will go on becoming more and more, it will be becoming still higher above synchronous speed. It will continue to increase. So there will not be any chance of the for the generator rotor to regain synchronous speed. Therefore, we can say that synchronous speed must be restored at this point or before this point is reached. So what we can say? We can say that the maximum decelerating area available to the generator rotor is BMCB. Okay, BMCB. This area represents the maximum available decelerating energy. Okay, so this can be extracted from the rotor, and if we can show that this area is either equal to this area or it is greater than this area, then we can say that for the first swing, generator's rotor will be able to restore synchronous speed. Okay, that has been done. So initially AGBA, this area has been calculated, then BMCB, this area has been calculated, and it has been found that BMCB, this area is much greater than this area. So we can say that generator rotor will be maintaining synchronism. So this has been done here. Okay. This has been done here. It was calculated 5.72 megawatt radian was the accelerating area, and available decelerating area BMC and then D, basically BMCD. This area is equal to 17 megawatt radian. So this ensures that this is much greater than this area. That means it indicates that generator will be able to maintain synchronism, and it will swing somewhere here up to this point. It will not move up to this point because it is much greater than this area. So where it will stop um, increasing delta, it will stop increasing delta up to that point where the synchronous speed will be restored. Maybe somewhere here it will be restored because there we can say that this area and this area here may be equal. So it will swing up to that point when the synchronous speed is restored. And then again it will start backward swing. Okay, it will move in the backward direction. But we are interested in the first swing only. So in the first swing, delta perhaps will be moving up to this point here. So now let us see, okay, so you can easily calculate this. So this maybe you can consider this as an example. So as a rather assignment, and you calculate up to what point delta will swing. Generator rotor, how much how long generator rotor will swing? What is the maximum delta for this particular condition for this disturbance, which is equal to 30 megawatt increase in the input power. Okay, so this was the first part. And again, we have added a second part here. What is the second part? Generator will be stable. Actually, not well prepared this one. Okay, it is stable. It is with the conclusion of the first part. Now, the second part is maximum permissible limit in prime mover input. Now, the second part of the example is what is the maximum permissible increase in the input power so that generator will not lose synchronism. Okay, what is the maximum permissible increase in the input power so that generator will be able to maintain stability. If the input power is too much, there will be, that means disturbance is too much. What is the input power? Suddenly you are giving an extra input to the generator, so you are applying a disturbance here. That disturbance, if it is too large, it will not be possible for the generator to withstand the disturbance, and as a result, generator may lose synchronism because speed will be become above synchronous. Then you will not be able to obtain an area A2 where the generator will be returning and this synchronous speed will be restored. Okay, so there must be some limited disturbance. Disturbance must have some limit. So we shall have to check here up to what limit you can increase the input power so that generator will maintain synchronism. Now we will note one point here. Here you see that generator is operating at this point. So what is the maximum disturbance that the generator will be able to withstand now? That depends obviously upon this operating point. Had the initial operating point been here, so obviously it will be able to withstand a smaller disturbance. Had it been somewhere lower here, so it would have been possible to withstand somewhat larger disturbance. So how much disturbance the generator rotor will be or the generator will be able to withstand and it will be able to maintain synchronism, that depends upon the present operating condition. This is very important for to understand the transient stability. Actually, in case of steady state stability, the ability of the system to maintain synchronism is independent of the operating point because it is the disturbance is so small that we are not actually we are ignoring any oscillations. So if the disturbance is so small that we can ignore oscillation, then obviously the stability limit will be indicated by the maximum permissible power output that is occurring at delta equal to 90 degree for cylindrical rotor machine. But for transient stability, where the disturbance is sudden, disturbance is large, how much will be the, you can say, the impetus on the generator because of a fault, because of a disturbance, that depends upon many things, one of which is the initial operating point. Okay, so we shall now examine what is the maximum permissible increase in input power at this point when the generator was operating at this point, such that the generator will be able to maintain synchronism. But I think you can understand that that disturbance or that magnitude or the answer that will be obtained by us, it is valid for this present operating point only. Had the present operating point is changed, the magnitude of permissible disturbance also will change. So you can say that transient stability does not have a fixed limit. Okay, what is the max limit of transient stability? No one can say because there is no such fixed point. There is no such declared stability limit. That how much the disturbance the generator will be able to withstand, that depends upon the present operating condition and some other things that we shall be discussing later on. Okay, now let us see for this particular machine how much disturbance it will be able to withstand. So for that, here what we are doing, we are actually finding area. So we are assuming that they say the disturbance will be up to point. That means input power increase will be such that the new power input line or new power output becomes equal to P1. So that P1 indicates the new power output line or new power input, new position of the power. Okay. So it would have been better if I could draw it again, but because of this limitation, I cannot draw. So I am explaining. So calculation, you see, you check whether you can understand or not. Then we shall try to explain if it is not understood by you. So P1 is the, we assume that P1 is the new power input up to which the disturbance may be or the input power may be increased. And 100 sine delta, 100 is the peak of the power angle curve. So what we are, you see that we are calculating some accelerating area. Why this is an accelerating area? Because P1 is the new one input. So P1 minus 100 sine delta indicates that input is greater than output. So obviously from delta 1 to delta 2, machine is accelerating. This is accelerating area. So from delta 1 to delta 2, input power is greater than output. The machine will be accelerating. What is that area? What is that energy? Or what is that area? That is calculated here. Now from delta 2 to pi minus delta 2. Now why pi minus delta 2 we are questioning? Because again coming to this point, you forget about the new operating condition. That means for this particular condition, I have explained that the generator rotor must regain synchronous speed at this point. So since we have to find out the maximum permissible power input, okay, so obviously at this new condition, if we assume that this is P1, then at this P1, the synchronous speed, if we want to find out the limit of increase, that synchronous speed must be restored just at this point, not before this. If it is restored before this, then it indicates that some more power increase will be possible. So since we want to find out the maximum power input, maximum possible power input without losing synchronism, then obviously the synchronous speed must be restored just at this point. So if it is delta 2, if B at B, angle is delta 2, obviously this angle is pi minus delta 2. That's why here we are integrating between these 2 points, delta 2 to pi minus delta 2. So from delta 2 to pi minus delta 2, you see that, so power output line, power angle curve has crossed this point. Power output line has crossed this point. Input power line, it has crossed. So in output becomes more than input. And what is the output? Output is 100 sine delta, this curve. So 100 sine delta minus P1. So output minus input. That means here we are calculating the retarding area. So we are calculating retardation area, available decelerating energy, such that it becomes just equal to the accelerating energy. We are interested to find out that delta around which the accelerating area and decelerating area will be same. Okay, and that angle obviously is delta 2. So delta 2 here is now that critical, so-called critical clearing angle that we have expressed previously. That means delta 2 is that angle up to which, that is the crossing line between the input power line and output line. And if the machine becomes stable, here the machine will become stable at this point. This will be the new operating point. Okay, between delta 1 and delta 2, we are finding out the accelerating area. Between delta 2 and pi minus delta 2, this is the decelerating area. This indicates that if the machine becomes stable, then new operating point will be this one, because around this point we have obtained this area equal to just this area. Okay, so this has been done. Rest are basically the calculations. So we will be obtaining this type of angle. Okay, where you will be obtaining this type of equation, 5 5 pi by 6 sine delta 2 equal to cosine delta 2 plus 0.866. So obviously we will be estimating some angle delta 2 and verify whether these two are equal or not. In this way, we have to check, we have to solve this equation. Okay, so this solution, you have to trial for different value of delta. You have to adjust the value of delta. In this way, using trial error method, you have to find out the value of delta. Cross solution will not be possible here. So we'll be doing this. And here, by doing this, delta P, that means increase in input power, that has been obtained to be 36.6 megawatt. That means initial operating point was corresponding to 50 megawatt power output. From this point, the maximum power increase line, maximum input power possible is 36.6 megawatt. So input power will be 86.6 megawatt. Obviously, at stable condition, the generator will be able to maintain stability. Yeah. What will be the output power? Obviously, it will be also 86.6 megawatt. So, new operating angle, therefore, will be the that point where the input power line and output power curve, they are intersecting each other. That first point, delta 2. Okay. So this is, I think you will be able to understand this. You will be able to solve it. This calculation you can do. I should not rather discuss all these things here, because in this mode that is rather it is not done, cannot be done properly. It is better done in the classroom where chalkboard and okay, blackboard and chalks are used. Okay. So now this is this thing. I shall then how to improve the stability I shall discuss. But before that, I am discussing another example here. That was an example where we have changed the input. Now consider another example. This example again is to give you a better understanding of the transient stability problem when we assess the stability using equal area criterion. That means how we shall be applying equal area criterion to explain different operating condition or different disturbances. How can we explain the stability of the system using equal area criterion? Okay. Now you see that here, what is this example? Here, a generator is given, okay, connected to a bus, and there is a double circuit transmission line. Okay, parallel lines are there, double circuit lines. This is one line having, say, reactance is X1, another line reactance is X2. Generally, already perhaps we have mentioned that within the resistance of the line is very small compared to reactance. So for many analysis of our system, sometimes we shall be ignoring the resistance. That's why we are neglecting resistance here. Okay. So this is the infinite bus. So generator is connected to a large power system, and the output of the generator is being delivered to the power system through double circuit line. So what is stated here in the example? A balanced three-phase fault occurs at the midpoint of line 2. These are the two lines. Reactance of this line 1 is X1, reactance of the second line is X2, and three-phase fault occurs at the midpoint of line 2. Somewhere here the three-phase short circuit takes place. When the power transfer is 1.5 per unit, so everything is now given in per unit. A base power was considered, and generator is delivering power which is equal to 1.5 per unit with respect to that base power. Okay, so let us talk in terms of per unit only. What is the base? It is not given. Since all data are given in per unit, we need not bother about that also, because we know the values which will be sufficient for us. Okay. If E is 1.2 per unit, what is the E? Is the generator. The generator, already we have discussed that. Why? What is the basically the model of the generator? Generator is represented with the help of a generated voltage in series with some reactance. In series with some reactance, we ignore the resistance for simplicity. Okay. Here that induced voltage is 1.2 per unit. Here you see that we are not considering the effect of change in field current. Generally, generators are equipped with excitation controllers, so that effect of excitation controllers are not being effect of excitation controller is not being considered here. That means we are assessing stability of the generator without considering the effect of excitation control. Okay, because we shall be doing with simpler thing first, then complicated things may be also dealt with. B is 1 per unit. That means the terminal voltage. Terminal voltage means in this case, basically this V indicates the this voltage, infinite bias voltage, 1 per unit. XD prime, it is XD prime. Okay, XD prime is 0.2 per unit. What is the XD prime? It is the transient reactance. Transient reactance. You know that synchronous machines may have three type of reactance, or synchronous machines are having three type of reactances. One is the steady state reactance, that is called the synchronous reactance. Is the during normal operating condition, this is the reactance offered by the machine to the flow of current. Okay, what is this synchronous reactance? It is leakage reactance plus armature reaction. Armature reaction during normal operating condition. You know that on the field flux, there is an impact of the armature winding flux. Armature current flows. Because of the armature current, a flux is generated. So that flux interacts with the field flux, and this interaction is called the armature reaction. And this reaction, this armature reaction, that is this effect of armature flux on the field flux, is represented in the form of some reactance, that is the armature reaction reactance, say XA. So leakage reactance plus armature reactance, this is the synchronous reactance. Okay. Now, during disturbances, what happens? During disturbance, armature current, say a fault occurs. When a fault occurs, what happens? Say a fault occurs at the middle of the generator. Then what will happen? Because of this fault, since the terminal voltage becomes zero, obviously there will be a large current. So a large disturbance occurs, a fault occurs, and generator is delivering large current. So now the question is, what will be the reactance of the generator under this condition? Will it be same as the reactance offered by the generator during?
Sir, you are not audible.
Now, hello. Now can you see? Can you hear?
স্যার ভয়েসটা খুব কেটে কেটে আসছে।
কেটে কেটে যাচ্ছে। বসে দাঁড়াও।
Now it's okay, sir.
এটাই ওকে। আচ্ছা আমাকে একটা তোমরা বলো, have you studied anything regarding the reactances of generators? That means the steady state reactance or synchronous reactance, transient reactance, and sub-transient reactance. Have you studied all these things? Do you know all these things? জানো কি? শুনতে পাচ্ছ তোমরা? বলো। হ্যালো।
স্যার রিপিট করবেন আরেকবার।
বলছি যে ট্রানজিয়েন্ট রিঅ্যাক্ট্যান্স, সাবট্রানজিয়েন্ট রিঅ্যাক্ট্যান্স, এগুলো কি এইসব টার্মিনোলজিগুলি কি তোমাদের জানা আছে? এগুলো কি শুনেছো তোমরা? বলা হয়েছে তোমাদের কোথাও না কোথাও? synchronous machine different types of reactance হয় তো, synchronous reactance is perhaps already known
Yes,
to
sir.
you.
Yes, sir.
And transient reactance, do you know what is transient reactance and subtransient
Sir, I
reactance? Huh?
Yes, sir. It is taught in the class of
Yes, sir.
symmetrical point.
Okay, so if you know,
हाँ sir, জানি।
so no, shall I explain what is this transient reactance, or you will be able to understand? Because here the generator is represented by generated voltage in series with transient reactance. It is XD prime. XD prime is the transient reactance. Why it is XD? Because basically this generator is a salient pole machine generator. That's why they are giving the direct axis transient reactance. Or do you call that this is the even if it is cylindrical rotor generator, say we are writing the transient reactance as XD prime. Okay, to differentiate between synchronous reactance and transient reactance, this prime is used here actually. Okay, and what's the meaning of this transient reactance? What is the reactance that the generator will be observing if a sudden disturbance takes place? If suddenly generator current changes, if a disturbance takes place suddenly. Okay, what happens if the disturbance takes place? Suddenly, there will be an increase in the armature current. So, let me discuss this transient reactance and subtrend reactance in brief. Okay, so that I shall be in a, it will be better for me also to explain things. Okay, so when suddenly there is an increase in the uh, output current of the generator, what happens? Armature current increases, means armature flux also will increase. Okay, but obviously in a magnetic circuit, flux cannot increase instantaneously. It is opposed by the system. As you know, in case of inductance, you know that in case of inductor, whenever you attempt to change current, an opposing EMF is created. Okay, an opposition is created. So here also, if you attempt to change the flux suddenly, it will be opposed by the system. How it will be opposed? When the armature current increases suddenly, armature reaction flux will increase suddenly. So this sudden increase in armature reaction flux will actually, or rather armature flux, will actually create EMF induced in the field circuit of the generator, and EMF will be induced in the damper winding of the generator. Now damper winding is a closed winding, circuited winding, and field circuit is there. Field winding is supplied by DC. So in the field winding of the generator, it will be the normal DC current flowing, but in the field winding, above over and above this DC current, there will be another EMF induced because of the change in the flux in the armature of the, because of the armature current of the generator. So what will happen? Because of this induced EMF, there will be some additional current flowing in the field winding of the generator. There will be some current flowing in the damper winding of the generator. Damper winding is a short circuit winding, so basically that current will circulate inside the damper winding. So additional flux is created. What is the role of this additional flux? This additional flux created due to the induced current in the damper winding and induced current in the armature in the field winding. They will oppose the very cause. What is the very cause here? The cause is the increase in the armature flux. So increase in the armature flux will be opposed by the additional flux of the field winding because of the induced current, and additional flux of the damper winding because of the induced current. As a result, resultant flux or resultant flux linkage will remain same. It will not change abruptly. It will remain same as the pre-disturbance period. Okay, but what happens? There is a sudden increase in current. So armature current increases, but armature flux does not increase because of the opposition. So if you calculate the inductance is flux linkage by current. So flux linkage remains same, but current increases. So inductance value calculated will be somewhat lower. So this inductance is the subtransient reactance of the generator. Okay, am I clear? So this reactance is the subtransient reactance. This inductance is the subtransient inductance, and this inductance obviously will be much less than the static reactance because there is an increase in armature current, but there is no increase in the resultant flux. Okay, now that the current has the EMF has been induced in the damper winding and field winding, that has occurred only once when the current was armature current was suddenly increased. So that is not a sustainable condition. So that will not persist forever. So that induced current gradually will actually die out. It will die down gradually. Okay. Additional current induced in the field winding, it will die down, taking a time equal to the time constant of the field circuit. Damper winding current also will die down, taking a time equal to the time constant of the damper winding. Damper winding resistance is somewhat higher. That's why that current will die down very fast. So initially, therefore, after few cycles, starting from the disturbance, after few cycles, this current will die down completely. Then field winding current, additional current, it would somewhat more time. So initially, therefore, the during transient condition, when the damper winding current is flowing, the reactances will appear to be much less. But gradually it will increase as the damper winding current decreases. So after 3-4 cycle, damper winding current will die down completely, and then reactance will change, you can say, because still the field winding current, the same field winding current is there. So field winding current will sustain for some more time, some longer time. So during that period, when the damper winding induced current is existing, that time is called the subtransient time. And that time, after that, that means when the damper winding current has died down, starting from there up to the achieving of the steady state condition of the generator, that period is called the transient period. That period is the transient time. Okay. So reactances will be therefore calculated accordingly. So obviously, the transient reactance will be somewhat larger than the subtransient reactance. Why? Because the damper winding opposition from the damper winding flux that has been withdrawn, but still the steady state condition has not been achieved. So before the steady state condition is achieved, and after the damper winding current is made zero, during this period it is the it is a transient period. During this time, what will be the reactance or what will be the inductance? It is the flux linkage divided by armature current. So armature current is high, flux linkage is somewhat more than the subtransient period, but it is uh, it is actually not the full flux linkage, because there is still opposition from the field winding flux. Okay, so again, if you calculate the inductance, it will be less than the steady state reactance. During transient stability study, the period for which the stability study has to be done, that means the period that will determine whether the system will be stable or not, is actually can be said that system will be on the generator will be in transient condition. That's why during transient stability analysis, generator has to be represented by its transient reactance. The transient period is too short, therefore we shall not be representing the, the generator using transient reactance, but the transient stability study or to determine whether the system will be able to maintain synchronism or not, it will require some time. It will swing for some time. That swing will be actually during that time when the generator is swinging, the reactance of the system, reactance of the generator may be represented using the transient reactance of the generator. That's why we shall be representing the generator using the generated voltage and transient reactance. Okay, we are considering that voltage to be fixed because we are considering the field current to be fixed. So induced EMF is fixed, and internal reactance of the generator reactance is 0.2 per unit, means this is the transient reactance. And it is given that x1 and x2, there are double circuit lines, both are having a reactance equal to 0.4 per unit. So this line is having 0.4 per unit reactance, this line is also having 0.4 per unit reactance. Now for this system you have to apply the equilibrium criterion to determine the stability of the system when some fault is occurring. What is the fault? Fault is a three-phase fault occurring on this line, on the second line, and somewhere at the midpoint of this line. So at the midpoint of the line, obviously this reactance will be 0.2 here. Here reactance will be 0.2. Okay. Now let us see what are the conditions given. A is that determine whether the system is stable for a sustained fault. That means a fault has occurred here, and sustained fault means that fault is remaining in the system. It is not being it is not been cleared by the system. That means the fault is remaining there. Circuit breaker that are connected here and here, they are not operating. This is the meaning of sustained fault. Okay, fault is there and circuit breakers are not operating. Okay, why we are analyzing this situation, explaining this situation, it will be apparent after some time. The fault is cleared at delta equal to 60 degree. Then second condition is the fault is not a sustained fault, it is cleared. And when it is cleared, when delta is 60 degree. Now remember, note that here the fault is cleared mean who will be clearing that fault. This does not mean that fault has removed itself. Okay, fault is a permanent fault. It has not been removed by itself. So it has been cleared means the circuit breaker at this end of the line and at this edge of the line, obviously in long transmission lines here, okay, important transmission line, these are high voltage line carrying hundreds of megawatt of power. Perhaps I don't know whether I forgot whether I have actually mentioned or maybe the power transfer capacity of a line. If say this is a long line, say the voltage is 400 kilovolt, then the power rated power is around 600 megawatt. So when this large amount of power is flowing through a line, it sufficient protection mechanism, protection system must be equipped with this line. And what is this protection system? It is the circuit breaker at this end and also circuit breaker at this end. There are relays connected with the circuit breaker. So when it is said that the fault is cleared at delta equal to 60 degree, it has been cleared by the operation of the circuit breaker. That means the circuit breaker here and here, they have opened this line. Fault has been removed. Fault has been isolated from the healthy part of the power system. This is the meaning of this fault clearance. Okay. Now you have to see when this fault is removed, that means faulty line has been removed, whether the system will be stable or not. If fault is cleared at delta equal to 60 degree, whether the system will be stable or not. If so, if it is stable, find the maximum rotor swing, how long the rotor will swing, how far the rotor will swing, what is the maximum value of delta. That has to be determined. Okay. And lastly, find the critical clearing angle. So if this fault is this situation, this scenario is found to be stable, then you have to find out, or even if it is unstable, you have to find out what is the critical clearing angle. Critical clearing angle means when the fault has to be removed, when the faulty line has to be disconnected, such that the system will be just stable. That means system will be able to maintain synchronism if the fault is cleared here. Okay. So what is the limited value of delta that will just retain the synchronism of the system? That angle you have to calculate. Okay. So this is a very informative but instructive problem. Let us follow this. Okay. So it is given that P before fault, that means peak of the power angle curve is given, it is before fault is 3 sine delta. That means how you will be calculating the peak of the power angle curve? Obviously, you know the induced voltage here. You have to calculate, take this reactance, then parallel combination of this reactance, so this generator reactance, plus parallel combination of these two reactances. They are in current in series, and here voltage is E 1.2 per unit. Here voltage is 1 per unit, so 1.2 into 1 by x, total reactance, summation of this reactance and parallel combination of this reactance. Okay, that becomes 3. Okay, P maximum becomes 3 under the normal operating condition. Okay, so P before fault is therefore 3 sine delta. During fault, what happens? During fault it becomes 1.2 sine delta. So during fault, what is the situation? Okay, here these are given, but sometimes you may have to actually calculate this values 1.2. So that's why I am explaining it here. What will be the P fault? That means during fault, what is the peak of the power angle curve? During fault, you see that fault has occurred here. So this portion is connected to ground. So from this bus, this reactance is connected to ground. From this bus, this reactance is connected to ground. This reactance is between these two buses, and the generator is represented by generation voltage in series with that reactance. So this is the circuit. You have to resolve this circuit. Then you have to find out what is the value of reactance between the generator and this infinite bus under that condition when this point is connected to ground. If you connect this, it is not very difficult. You have to convert star into delta or delta into star do of the impedances, and you'll be finding that P fault becomes 1.2 sine delta. Naturally, power transfer capacity of the system will be much less with the fault in the circuit because much of the current will flow through this branch to ground. Okay, voltage here will be reduced to a very lower value, or a part of the power will be flowing through this healthy line. That's why it becomes 1.2 sine delta. And after the fault means after the clearance of the fault, after the faulty part is removed, then after the fault what happens? This line is disconnected, this line is disconnected. Then calculation becomes simpler here because now generator then um, generator reactance plus this reactance. This is the only circuit here. So that voltage, this voltage 1 and it is 1.2 divided by zero point 0.2 is the transient reactance plus it is how much? It is zero point 0.4, zero point 0.6 is the total reactance. So 1.2 into 1 by zero point 0.6, it becomes 2 sine delta. That's why it is coming like 2 sine delta. Okay. So see that 3 sine delta perhaps you will be now able to do it because x1 and x1 in parallel means it is zero point 0.2. So zero point 0.2 plus zero point 0.2 here, zero point 0.4. Okay. So 1.2 into 1 by zero point 0.4 means 3. 3 sine delta is coming in this way. 2 sine delta is coming in that way. I have explained. And 1.2 sine delta because of these reactance from this bus to ground is zero point 0.2. From this bus to ground to zero point 0.2. So you have a reactance here, you have another reactance here, you have another reactance here, you have another reactance here. This reactance from this bus to ground will have no impact on the power flow of the line. So what is there? You have a reactance from here to ground, a reactance from here to here, and a reactance here. So basically now from this point to this point, what is the transfer reactance? That you have to calculate. So this star you will be converting into delta. To convert into delta, you will be finding some reactance. So that voltage here 1.2 into 1 divided by the transfer reactance, it will be coming to be 1.2. So in that way, the during fault condition, power angle curve is represented by 1.2 sine delta. Okay, so I hope you will be able to do this. So once this is given, now you apply the given condition. First of all, determine whether the system is stable for sustained fault. Okay, so let us draw this. This is the 3 sine delta curve before fault. This is 1.2 sine delta. It is the during fault, and it is 2 sine delta after the fault clearance. What is the initial operating angle? Initial operating angle, you see how much was is the power delivered 1.5 per unit is the power being delivered before the fault. Peak of the power angle curve is 3 sine delta. So it is 1.5 power input line and power output must be same. That's why it is 1.5 per unit is the input power line. This curve is 3 sine delta. This is here it is 3. So operating point here obviously will be delta 0 will be equal to 30 degree. It will be 0.5. Okay. So now if now this is the operating point delta 0 and the fault occurs, suddenly the three-phase short circuit occurs, then this becomes the power angle curve, output power line. Input power is here, output power follows this line, this curve. So you see that here input power, you see that it is always greater than the output power line. Okay, can you follow? Input power is 1.5, and if the fault is sustained, first condition, if the fault is sustained, you see that output power line power curve is always this one, which is peak is 1.5. Sorry, peak is 1.2, always less than the input power line. So if the fault is sustained, we can say that without any calculation, by observing the values only, you can say that the system will become unstable. Okay, the system will become unstable. Is it clear to you or not that for a sustained world, the system will become unstable? There is no question of maintaining stability. Is it understood by you or not? বলো বুঝতে পেরেছো that for sustained fault the system will become unstable? Is it clear or not?
Yes, sir.
Yes, sir.
Why it is unstable? Because you see, input is always greater than output. Always there will be acceleration. There is no question of any deceleration. So if there is oscillation always, when the fault is sustained, when the fault is not removed, then how the speed will decrease? It will always become synchronous, above synchronous, and it will go on increasing until the stability of the system will be lost, and generator has to be disconnected finally. Okay, so under the sustained fault condition, system will become unstable. Okay, so this is the answer for the first time from observation only. You can say that, and this is the explanation why the system will become unstable, because always input power is greater than the output power. Now, what happened in the B condition B? The fault is cleared at delta equal to 60 degree. Whether the system will be stable or not. So somewhere here the fault is cleared. It is 60 degree. This is 90 degree. So now the when the fault is cleared, this will be the operating point, operating power angle curve. So before the fault, this was the power angle curve. If the fault is there, this is the power angle curve. That means operation will be on this curve only. And after the fault is cleared, that means from 60 degree here, this will be the power angle curve. That means this curve will be followed by the generator. Now, if the fault is cleared here, say from delta equal to 30 degree to delta 0 equal to 30 degree to this delta 60 degree, between these 2 points, you see that input power is greater than output power. This is the output power because fault was there. This is the input power line. So output is less than input. So this area A1 represents the energy inserted into the generator rotor. So this is the accelerating area. Let us calculate this. How much is this area? It is given by A1. It is 1.5 minus 1.2 sine delta between 0.520 in radian delta 0 to 60 degree 1.048 radian. You calculate the value of this area, that is 0.346. This is per unit megawatt radian. Power is in per unit megawatt and angle is radian, so per unit megawatt radian is the area A1. Now we have to check whether the system will be stable if the fault is cleared at 60 degree. How to check it? If the fault is cleared at 60 degree, then you see that the system will become stable if the generator delta will actually swing following this curve, and synchronous speed must be restored at this point or before this point is reached. Then only you can say that generator will be able to maintain synchronism. Generator will be able to maintain stability. That means for the generator to be stable, synchronous speed must be restored at this point or before that. So we have to just check. We want to merely check whether the stability will be possible or not. To check, what we shall do, we shall see how much is the area available here. If we see that this area available is greater than this area or equal to this area, then we can say that the system will become stable. So that's why this area will be calculated A to max. So that means maximum permissible or maximum available decelerating area. Why we are saying this maximum available decelerating area? Because here the generator will decelerate from the speed it has achieved here. So from this speed it will decelerate, and finally let us see how much is the area here. If it is greater than this area, then we can say that stability will be achieved. Even if it is equal to this area, then the stability will be achieved. So calculate this 2 sine delta. This is the 2 sine delta is this curve, minus 1.5 is this power line. So here output is greater than input. So here the retardation area, retarding it. So 2 sine delta minus 1.5 d delta integration from 1.048 to pi minus delta 2. It is if it, or it is delta 1 say. If it is, so this angle you have to calculate. This is input power line and output power curve. They are meeting at this point. So this angle is, say, it is, they have written is delta 1. So this is delta 1. This angle will be pi minus delta 1. That's why 1.04 swing is starting from here. Deceleration, that swing. 1.048 to pi minus delta 1. Between these two angles, what is the area available. You calculate, it is 0.453. It is coming to be minus. Minus sign indicates that it is actually retarding area. Actually, when you calculate it, it is 0.453 is the magnitude. It is greater than this area. That means the system will be able to maintain synchronism. Okay, so A2 max, maximum decelerating area available is greater than accelerating area. So obviously the generator will be comfortably maintaining synchronism. Comfortably it will maintain synchronism. Okay, so that is ensured from these values. Now to find out the maximum swing, it is given. Part of the problem is, you see that part of the problem is, if so, find the maximum rotor swing. How much the rotor will swing? That means we want, it will not. That means the synchronous speed will be restored before this point is reached. So we have to find out at what angle that synchronous speed will be restored. That is the maximum rotor swing. Okay. So that angle is delta 2. So that angle is delta 2. So what we shall do, we shall start integration from 1.408 and integrate up to delta 2. Okay, up to which the rotor swing. So let us integrate between these 2 points. 1.5 is the input power line. You can write peak of the pump, the 2 sine delta minus 1.5 or 1.5 minus sine delta. Only the sign will be different. Okay. So 1.5 minus 2 sine delta, integrate between this point and somewhere here say delta 2. If you calculate, then this is the expression you are finding: 1.5 delta 2 plus 2 cosine delta 2 equal to 2.225. Now we have to solve this angle. Maybe it will be somewhat difficult, but this solution is needed. Okay, so it will not be very difficult for you. Nowadays, when will be you will be using calculator, and no problem will be there. So you can calculate this, but this is the way how you can find out the maximum rotor swing and what is the implication of the maximum rotor swing. It indicates that at delta 2, the synchronous speed will be restored again. Generator will swing up to that point only. And that point, from calculation, you will be finding to be 105.88 degree. Now note one thing here. Stable, what is the limit of stability, stability? That is delta equal to 90 degree. But you see that this generator, during swing, during transient condition, it is actually crossing that 90 degree. But this is not the stable operating point. This is the maximum swing. That means it may cross 90 degree. But if the system is stable, it will be coming back to an angle when that angle is less than 90 degree. And there the system will be running at stable condition. Okay, so 105.88, this is the maximum swing, but the stable point will be always less than 90 degree, a point which is less than 90 degree. Okay, but during transient, during swing, generator may cross that limit because it is in the swinging condition. It is now in the unstable, it is now oscillating. It may exceed 90 degree during oscillation, but the stable point, if it is becoming stable, stable point should be always 90 degree or below that. Okay, now this is the second part is completed. Now the third part, find the critical clearing angle. This is also not very difficult. Critical clearing angle, how to find out? Now you see that generator is swinging up to 105.88 degree or 1.848 radian. Okay, but this angle is greater than this. This angle is greater than 105.44, 105.88 degree. That means now you have to find out the fault has to be clear such that the generator will swing up to this point. That means maximum rotor swing will be just this point. That angle you have to find. So this is not difficult, this is not difficult because you are now finding this angle will be variable now. This angle is variable. Say delta, if it is delta considered to be delta C is variable. So now you integrate 1.5 minus 1.2 sine delta between 0.2, 0.5 to 4. But this one to this angle say delta C. And this is accelerating area. What will be decelerating area? So the accelerating area now we want such that it becomes just equal to this decelerating available decelerating area. So it is delta C to 2.293. Why it is it is delta C to 2.293? Why it is 2.293? Because you see that this line is known, this angle is known. When this angle is known, up to which the generators may be allowed to swing, that angle is also known because it is pi minus this angle. Okay, pi minus this angle. So this angle is known. All right. So you are now changing this angle. Okay, changing this angle, but this angle does not change. So this area is changing. Area is changing. Okay, but not this point is changing because its peak of the power angle curve is fixed. So this point is known. That is it. That's why it is 2.293. So now you equate this to area, and you will be finding delta C to be 68.6 degree. That means the clearance of the fault may be delayed up to this angle, critical clearing angle. This means then how far or how long you can wait, or how much time you can permit to the protection system for clearing the fault. We are not finding this in terms of time, rather we are finding it in terms of angle. So if you know other parameters, then obviously you can calculate the time also. Okay. So from here you see that one thing you can understand from here. You see that we can calculate some angle up to which we can allow the fault to be in the system. If the fault is cleared at this point or before this point, because it was cleared before this point in the second case when it was cleared at 60 degree. Now it is coming to be 68.6 degree. That means fault may be allowed to be in the system up to delta equal to 68.6 degree. And if you disconnect the fault, if you clear the fault before this angle is reached, then system will remain synchronism. System will be able to maintain stability. That means there is a maximum permissible time at which or before which the fault must be cleared. That means the steady state, the transient stability, that depends upon the fault clearing time as well. Whether the system will be able to maintain synchronism or not, that depends upon the speed of the protection system also. Why we are saying that the system, it depends on the speed of the protection system. It means the speed of the protection system for this example is should be such that it can clear the fault before this angle is reached, before 68.6 degree of the rotor angle is reached. So what we can say, how much disturbance the system will be able to withstand, that also will depend upon this fault clearing time. That means faster the clearance of the fault, faster your protection system, faster your speed of circuit breaker and relay, better is the transient stability of your system. That means better transient stability means your system can withstand a larger disturbance in power. So upon which factors it will depend whether the system will become stable or not. It will depend upon the initial operating angle that we have explained. It will depend upon the speed of the protection system. That is very much clear from this critical clearing angle. Okay, so is this point clear, or have you understood this example here? Any doubt, any confusion? বলো, কোনো কনফিউশন আছে বা কোনো ডাউট আছে?
স্যার ডিউরিং ফল্ট স্যার ট্রানজিয়েন্ট রিঅ্যাকট্যান্সটা কি করে ক্যালকুলেট করব এটা স্যার একবার বলুন।
During fault reactance, actually it would have been better if I could draw it, so I am explaining it. You see that during fault, this is the machine. How to represent this? This will be represented by this generated voltage plus synchronous reactance. That means voltage here. Where is this voltage? We actually are representing per phase basis because it is a three-phase fault.
Yes,
we represent per phase basis. So as if that means voltage is 1.2. That means from the ground neutral is ground here. From the ground to generator EMF, that is, it is a potential difference of 1.2. So here is the, so E is 1.2. Along with is the series reactance of 0.2. So here reactance is 0.2. Here it is 0.4. And from here to ground, what is the reactance? 50% of this line, it is 0.2. So you have a star connection 0.2 here. Okay,
Yes.
point here to ground and here to here point. So if this star is converted into delta, that means from the terminal of this induced EMF to the infinite bus, you will have one reactance. Okay, from this delta star started this one impedance here, another impedance here, another impedance here. From here to here, the reactance you can calculate. This reactance plus this reactance plus product of this to this. Okay, in this way by divided by using the conventional technique, you can find out this reactance. So you'll be in a position to calculate how much is the reactance from the terminal of this 1.2, this much of per unit voltage to infinite. Okay, another reactance will be calculated from here to ground, from the terminal of this 1.2 to ground. Another reactance is, okay, one reactance, second reactance, another reactance is, there are three reactants. Basically from here to ground one and from here to ground one. So any reactance from this bus to ground will have no impact on the power flow between these two terminals, between this generator and this generator. The reactance that has been connected at the terminal of this induced voltage to ground, this also will not help delivering any power from generator to infinite bus. It will deliver any current from generator terminal to ground. Current will flow, not the power. What will determine the current power flow from this generator to infinite bus? That is this reactance, terminal of this 1.2 to this bus. Okay, and that reactance will be the star to delta, this conversion reactance that will be obtained from this terminal to infinite bus. Could you get this point?
Yes, sir. Yes.
Okay, that will be coming to be like this as 1.2. Actually, that reactance perhaps it is 1.2 sine delta. That reactance will be actually how much? It will be 1 basically. Okay, this reactance plus this reactance and this parallel combination ultimately it will be 1, and that's why it is coming to be 1.2 sine delta. Is it clear?
Yes, sir.
Now, any other question, any other doubt regarding this example? Because this example, I already told you that this is very rather instructive example, because many things because regarding the transient stability and its determination, a better understanding of the transient stability problem is possible if you can understand this example clearly, and also the previous example that I have explained. These two examples are chosen for this purpose because they will give you a better understanding of the transient stability problem. So could you understand both the problems very clearly? Then I shall go to discuss the methods for improving transient stability or methods for improving stability in general. Is it clear? Both the example?
Yes, sir.
Okay. If you have no doubt, then let us discuss few points regarding the improvement of transient stability, because I shall be taking your class up to 12:30. So all the points, because much actually discussion will be needed here. These are the points we can identify are responsible for the stability, or these points are having impact on the steady state as well as transient stability of our system. So let us now see some of these points, and remaining we shall be discussing in our next class. Now you see that regarding stability, what is the rotor equation? Showing equation is m d2 delta dt2 equal to pa. Pa is the accelerating power, delta is the power angle curve, and m is the angular momentum. How we calculate angular momentum? It is I alpha. I is the moment of inertia and alpha is the acceleration, angular acceleration. Okay. So I, moment of inertia, that depends upon the inertia that depend upon the mass weight of the rotor. Okay, so you see that m d2 delta dt equal to pa. So if you see that if the rotor is heavy, if the inertia is more, then what will happen? The increase in or acceleration of the generator rotor will be somewhat less for the same amount of weight. So accelerating power is there. On what factor accelerating power will depend? It will depend upon what is the power output, what is the load, and how much is the disturbance. That will decide the accelerating power. You have no control over that. But because of that accelerating power, because of that PA, difference between input and output power, how much acceleration that power will create, that will be decided by the value of m. So obviously, if you have higher inertia, that means if the rotor mass is more, obviously inertia is more, and in that case acceleration will be less, and obviously then the tendency of the rotor will be to increase because the acceleration is less, and that will the more time to apply some control on the generator to restore synchronism, to maintain stability. Okay, that means if the inertia is more, the inertia is high, then you are in a better position to maintain the stability of the power system because you have more time to apply the controls. From that sense, we can say that high inertia will help maintaining transient stability. Okay, is this point clear? Okay, and low reactance. Low reactance. Why low reactance? Because how we represent the generator? Induced EMF plus some reactance. So if the reactance is low, obviously peak of the power angle curve will be more. Am I clear? Peak of the power angle curve will be more. So if the total system reactance is less, it means the peak of the power angle curve is more. What is the impact of this peak of the power angle curve? Any idea, anybody? Why you can say that if the peak of the power angle curve is more, it will be we shall be in a better position to maintain stability of the system. How it depends upon the peak of the power angle curve. That means how low reactance will help maintaining system reactance better, system stability better. Anybody can you guess?
The
Bolo?
steady state limit of the power
Steady
limit increase.
state the steady state stability limit বেশি হলে ট্যানজেন্ট স্টেবিলিটি লিমিট বা ট্যানজেন্ট স্টেবিলিটি মেনটেন করতে কেন সেটা শুরু হবে ওয়াই ইট
এরিয়াটা
ইজ
বেশি
হ্যাঁ
পাওয়া যাবে, এরিয়াটা
হ্যাঁ
বেশি পাওয়া যাবে, এরিয়াটা বেশি পাওয়া যাবে, ডিঅ্যাক্সিলেটিং এরিয়া।
এরিয়াটা বেশি পাওয়া যাবে শুধু নয় অ্যাকচুয়ালি for the same power to be delivered by the generator operating angle will be less, initial operating angle will be smaller. If the power angle curve is having a higher peak, same power may be delivered using a smaller angle. So since you are using a smaller angle, you will be getting more time. Angle is smaller means reaching the final maximum power swing permissible angle that will be far away from the initial position. That means you will be getting more time. More time means we have not yet considered any control here, but you have to apply some control for maintaining the transient stability. So that control, for applying that control, you will be getting more time. That means that controls, when applied, they will get more time to make the system stable. Therefore, if the initial angle is smaller, obviously system is in a better position. High inertia will help maintaining system stability. Low reactance of the system. Also, low reactance means obviously of the generator and the everything. If that is also small, then it will be in a better position. Generator will be in a better position to maintain synchronous operation. Okay. So that's why high inertia will help maintaining stability. Low reactance also will help maintaining stability. Then any measure to increase the steady state stability will help transient stability. Okay, whatever mechanism you may apply for improving the steady state stability. Everything will help to improve the transient stability as well. Okay. And what are the mechanism we can apply improving transient stability? Improving steady state stability means basically improving the peak of the power angle curve. So how you can increase the peak of the power angle curve? You can increase the value of E, induced EMF. You can increase the value of V. So these are the possibilities, but the system is that you actually are not having much control over these things, because V you cannot change. You can actually maintain good voltage, but what is the system voltage, that will be decided by some other things. But whatever the system voltage is there, that voltage should be properly maintained. That is what has to be taken from here. That means increasing the value of E and V means basically you will be maintaining better voltage. That means voltage regulation of the system will be better, has to be maintained better. To control the system in such a way that voltage is always very close to the declared voltage. Then the peak of the power angle curve will increase, and if the peak of the power angle curve increases, hmm, then obviously system steady state stability will increase, and increasing steady state stability will help improving transient stability also. Why? Because already I mentioned that higher value of the steady state stability limit means lower value of the initial operating angle, and smaller the initial operating angle, larger the generator will get before it uses synchronism. Okay, so then you will be able to apply the controls in a better way. So that's why increasing the steady state stability will help improving the transient stability also. Okay, so remaining points I shall be discussing in our next class. It will be reducing x, not reading. Reading not x, reducing x. Okay, so let us stop here today. I will be sending you this before correction, and I shall try to again send you this after correction. Okay, because then it will be helpful for you. So let us stop today, and we shall continue in our next class. Whatever things are left, we shall continue in our next class. Okay. Until now, whatever I have discussed regarding stability and whatever I have discussed today, if anybody of you are having some questions, you can now make me. I can try to explain those points. Otherwise, I shall be calling your names now. Bolo, কোনো question আছে? So if no question is there, then let me call you names. Abhishek Mojumdar,
Present, sir.
Aditya Rai,
Yes, sir.
Omrita Dotto,
Yes, sir.
Anirudh Anand,
Yes, sir.
Arijit Pal,
Yes, sir.
Arnav Pal,
Yes, sir.
Dipankar Singh,
Yes, sir.
Dipten Mardi,
Yes, sir.
Dia Rai,
Present, sir.
Kanishka Bhasak,
Present, sir.
Kaushik Maji,
Yes, sir.
Manos Patra,
Yes, sir.
Mujahid Alam, Mujahid Alam, Parvez Musharraf Sheikh, Parvez Musharraf, Sandeep De,
Yes, sir.
Yes, sir. Parvez Musharraf
Shankar
Sheikh.
Mitra, Parvez, you have responded, okay, and Sandeep De, okay. Shankar Mitra, okay, you are present. Shreyas Gadpati,
Present, sir.
okay. Arman Hossein,
Yes, sir.
Arman, okay. Mohammad Sohail,
Yes, sir.
Somnath Pal,
Yes, sir.
Saurabh Burman,
Yes, sir.
Sukesh Murmu,
Yes, sir.
Swapnil Kisku,
Yes, sir.
Ujjwal Haldar.
Yes, sir.
Okay. Anybody who could not respond? Ritam Khamru.
Sir,
Okay.
Parvez
Ritam
Musharraf
Khamru, you are
Sheikh.
present. Okay. Parvez Musharraf, you are present. Okay. 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 Thank you then.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.